So this is going to be our second video on motion in one dimension, and what we want to do in this video is we want to develop some equations for motion that are useful under the conditions of constant acceleration, which means we have an a that does not change, an acceleration that does not change in time. And this is good because all the cases that we examine will be these constant accelerations, as most cases are. So what we want to do is we want to start with our equation for acceleration, the fact that a is delta v over delta t, and what we want to do is we want to use and kind of change up our notation a little. And what we're going to do is we're going to say that v2 now goes to v. We're going to say that t1 is now 0. So we'll always start at t1 assuming our stopwatch is reading 0, 0. And then we'll go to some t2. The other thing we'll say is that v1 is now called v0. So we're going to say that our essentially v0 stands for our velocity at time equals 0, which is t1. And what this allows us to do, and then we're going to say that t2 is some t on the stopwatch at some point later in time when we make our reading for v. And this will allow us to rearrange our equation to say that at is equal to v minus v0, or that our velocity at some point in time, is equal to our initial velocity plus our acceleration times the time it's applied. So this is going to be our new notation that we're going to use, where v2 went to v, t2 goes to t, t1 is now 0, and v1 is now v at time 0. We're going to do the same thing. We're going to apply the same notation shift to our average velocity. So we said that our average velocity was delta x over delta t. So we're going to now make the claim that x2 now goes to x, t2 now goes to t, x will say that t1 now goes to 0, and x1 now goes to x0, or x at time 0. Then we can rearrange this. We can move the t to multiply it by the average, x minus x0. So our new position is equal to our original position plus however long we have our average velocity in time. So using these new notations, we're going to derive some equations that explain to us our position and velocities and locations, our equations of motion in 1D under any condition. So what we're going to do is we're going to start by saying that the average velocity can also be thought of as our v plus v0 divided by 2. And this is going to be fine because if we're thinking about our velocity, we can look at them if we take the average of 2 points on a line. So if we look at 2 points on a straight line, if we look at point 1 and point 2, the midpoint is always going to be between those 2 points on the line. So that's why we can call v the average of those 2 points. And we could also look at it graphically by looking at the acceleration equation, and we know that that v is equal to at plus v0, and if a is constant, you'll get this if we plotted. Now if we're thinking about this being time and this being our velocity, then the a is the slope, a equals the slope, and then we know that our point is the midpoint on the line because it will be some line because this has the form y equals mx plus b. So this will be one of our equations that we're going to need So we are now going to use that plus some previous information, and we want to be able to derive generalized position and position-based equations, because we can think about the fact that initially what we've had is we have x is equal to x0 plus v average times t. But if we have an acceleration, v now changes with time. So if a is not equal to 0, v changes. And then you can't use this equation. We would need some new equations. So let's look at how we can come up with some equations. So we'll start with this. We'll start with this equation here. Our position is equal to our original position plus our average velocity times time. And so to account for the fact that our velocity is changing, what we want to do is we're going to substitute in this new average velocity, which accounts for the fact that we're having some acceleration. So we plug this into there, and we get this new looking equation here. So let's see where this takes us. And so we have this average, and what we're going to do is we're now going to plug in our new velocity that has our acceleration accounted for. So this is going to be replaced with this, and this is now sitting here. So what we can do is we can now look at we can now clean this equation up a little, because we can group these two. So we add v0 plus v0, that's 2v0. 2v0 divided by the 2 gives us 1v0. 1v0 times time gives us this term. That leaves us now with this. So we've accounted for those pieces. Now what we want to do is we want to take AT times t gives you the 1/2 AT squared. So we have a new position equation. We have a new position equation here that our original position plus our initial velocity times time plus 1/2 our acceleration times time squared tells us we're going to be after the acceleration and velocity have been applied. So we now have a position equation that accounts for our accelerations. So this is a good equation. And this equation has all the other information buried into it, including your accelerations and velocities. So let's come up with another equation. The next equation we want to be able to not have any time in our equation but know what our position is if we know some velocities and accelerations. So we have these two equations from before, well, this equation from before, and we're going to solve this for t. Then what our goal is now, we can take this equation here and put it in for the t there. So let's do that. When we do this, when we take this and plug it into here, we now have this. What we're going to do is we're going to take v plus v0 and multiply it by v minus v0. So that's going to give us v squared minus v0 plus v0 minus v0 squared. So you can see these two terms will cancel each other, and that leaves us with this, which goes there. And so what we can do to go from this equation here, over to here, what we do is we move the x0 over to here, and that gives us our x minus x0, and that's going to be equal to v squared minus v0 squared over 2a. We now multiply both sides by 2a, and that leaves us with 2a times x minus x0 equals v squared minus v0 squared. Then we just add the v0 squared over and we get this end result. So this is our next equation that we have for knowing our position that doesn't involve a time. So we can figure out our position if we don't have a time, as long as we know the acceleration and some velocity information. The other thing that this would be useful for is knowing your velocities if you don't know the time, but you know your acceleration and how your position changes. So essentially now we have these four equations. We know that how our velocity changes with acceleration. We know our position as a function of time, given the acceleration and initial velocity. We now have this equation for our average velocity. We include it because it's going to be the basis of how we derived the other equation. And then we have this last one that's our time independent equation, so we can know the position or velocities. If we know the velocities and acceleration, we can calculate the position. Or if we know the position and the acceleration, we can know some information about the velocities without needing to know time. So these are going to be our four equations that we can use to solve motion under constant acceleration in one dimension. So whenever we want to solve problems in one dimension, make sure you carefully read the problem. Then I recommend you read it again to make sure you understand what's going on. You should decide on what information is important. Draw a picture to help you understand, and then put your axis on so you have a general idea in your mind what the problem looks like. Figure out what you know and what you don't know and what you're looking to solve for. Then think about the physics you have and plan your approach to solve for that unknown. Many times when 1D motion, there's a couple different paths you can take to solve the system, and they're all valid solutions. Once you've figured out the physics involved and what you can take advantage of, you need to choose the equation and then solve for your unknowns. Now these can be multiple steps. It's not like saying it's always going to be one step. You may have to find the time and then use the time to find something else. Or you may have to find some speed to then get the acceleration, or you may have to do several steps here. This could be several steps. It's not always going to be one step. Then to check your answer, you can check your dimensions and sig figs and make sure that it's reasonable. And then again, always check your units again. If your units are wrong, that means you've probably solved for the wrong thing. So this is our general preview of the equations for 1D motion and how we can approach problems.